Okay, I think we can start.
Yes,
Hello,
sir.
everyone. Good afternoon, and welcome to today's lecture by Dr. Ratheesh Kumar from Cochin University of Science and Technology. His main research focus on solid earth geophysics and hard rock petrology, and he's also interested in global tectonics. In this lecture, he'll be talking about evolution and geodynamics of lithospheres on Earth, Moon, and Mars. I hope all of you will enjoy today's lecture. So, Dr. Ratheesh, please carry on.
Thank you, Dr. Akira. Thank you all. Good afternoon from Cochin, from India. I would prefer if you could switch on your videos so that I can see you. We can just interact each other. So today I will talk about, rather it can be a discussion session. At any point of time, you can just interrupt me. You can just raise your hand and you can ask your questions. If it's a short answer, I can just immediately answer. Otherwise, we can have a discussion after the lecture. Hope it sounds good. First of all, the students, can you hear me? All of you, am I audible to all? I hope at least a few of you can respond.
Yes, sir, you are audible.
Thank you so much. Appreciate. Okay, so, well, the topic is right here, a comparative study of the evolution, physio-chemical properties and geodynamics of the lithospheres on Earth, the Moon and Mars. So it's a comparison. Let's see how different is our Earth from our nearby planet, the Mars, and our own Moon, the lunar planetary body. Well, so you can, the title slide itself shows, like, the Earth is there and Mars is here and our Moon is there with the comparative scale of their size as well. So you can see, we can figure out the Mars is half the size of the Earth, and the lunar body, the Moon, is even the smaller planetary scale body, but it's not a planet, it's a moon, right? Okay, let's move on. So you know what it is. This is our solar system, which consists of our star, the sun, and we have a nearby planets, and we have a distant planets. Those are discriminated by or delineated by the asteroid belt. Well, the interior planets, inner planets, they are also called the terrestrial planets. They include Mercury, Venus, Earth, and Mars. And the distant planets, they collectively called as the Jovian planets. So what's the difference between the terrestrial planets and Jovian planets? The terrestrial planets, they are having a rocky outer layer, a brittle rocky outer layer. All of them are having, including our Moon, right? But the Jovian planets, they are mostly composed of the gas materials, right? So that's the difference between the Jovian and, well, we are interested to discuss about the Earth, the Moon, and the Mars. But before that, we have to understand how these materials evolved, how these planetary scale bodies, they formed, and what is their composition, and how the composition, like the atoms, the material that made up of these planets, how they formed. So for that, I will take you back into the evolution of the universe. You know how the universe evolved, I guess. Well, it was originated from a point source, from a Big Bang. So this particular image, the diagram, it shows the evolution of the universe. Well, so this is the Big Bang. So this is at about 3 minutes after the Big Bang. Okay, so it is like, first a Big Bang explosion happened and nothing could exist at that stage. High temperature, extremely high temperature, nothing could persist. So only the photons were able to produce at that time. these photons were fused to form the matter and antimatter. And this matter is having the positive charge, antimatter is having the negative charge. So this matter, the positive charge, that's equals to the protons, and they fuse to, so they are equals to the hydrogen atoms, right? And at high temperature, these hydrogen atoms, they fuse with the neutrons to form the next hydrogen level. So that's called nucleosynthesis process. So this is what happens. One proton, that is the hydrogen, that is fused to with the neutron to form the next isotope of hydrogen, the higher form of hydrogen, that is deuterium, and plus some release of some gamma that's in the form of energy. And this deuterium combined with the neutrons to form the next level of the isotope of hydrogen, that is tritium, and so on. And the tritium with one proton, they fuse to form the helium. And finally, what formed is the lithium. So if you can see this slide and the periodic table over here. So this is after 3 minutes of the Big Bang, you know. So what you could observe is like only 3 elements, mostly hydrogen, then helium, and a little bit of lithium maybe. So this was the periodic table form, like the elements formed right after the 3 minutes of the Big Bang. So after that, what happened? A dark age happened. So after 3 minutes, the nucleosynthesis process completely shut down. It cooled off. And what happened? All these gases, that is hydrogen, helium, and a little bit of lithium, they just distributed across the universe. And they just fall into some star-forming regions or galaxy-forming regions. They collisit into the galaxy-forming regions, and they started to evolve like galaxies. And here, about 200 million years after the Big Bang, here forms the first stars and galaxies. And then our modern universe started to evolve. So from this clouds, you know, from the galaxies, what happened? The stars formed, or the protostars formed. And from that protostar, stars formed, and that stars grow into huge sizes. That's called red giants. Okay. So that red giants, so this is a red giant actually. So this is an old star. So the red giants are the old stars, those grow into great volume. And during that greater in sizes, they are growing large. What happens? Their core is getting more denser and denser, more high temperature and high pressure happens. And here, during this time, when the core was getting heavy, the elements on the periodic table up to iron formed at that time. And after that, completely the core has been collapsed due to gravity instability, and that has been exploded. That exploded like a supernova. So that exploding of the red giants are called supernova. So during that supernova explosion, all other elements, for example, here you can see like, you know, carbon fused with helium to form oxygen, helium fused with oxygen to form neon, up to iron was formed when the core was heavy. And after that, the supernova explosion happened. And during that explosion, all other elements in the periodic tables, they formed, so that these all other elements, the later formed elements, they occurs in trace amounts. Like, for example, gold occurs in trace amounts, right? So uranium, they occurs in trace amounts, right? So these elements formed during a very fraction of a second during the explosion of supernovae. And these materials again distributed across the globe, and again they fall into star-forming regions. The solar systems captured these elements, and finally, what happened? This is the thing, the solar system is evolving here. A protostar is forming somewhere here. Okay, so they have, why they are called protostar? Because the nuclear fusion process has not started at this point of time. But when it attained a particular temperature, high temperature, the nuclear fusion triggered, and that will light up the sun. And during that process, all the material. So it formed like a disc-shaped geometry with all the dust particles, gas particles, everything formed like a disc-shaped geometry around this protosun because of the centrifugal force. And finally, when the sun lighted up with the nuclear fusion process starts, what happens? All the lighter materials, they whisk away from the sun, and they form like on the disc-shaped geometry, they form like the planetary scale bodies, and that's how the Jovian planets form, that is the outer planets form. And all the denser particles, they remain within the vicinity of the sun, and they just form their own small accretionary. You can see here, small dust particles, small fragments are accreting onto larger particles, bombarding and forming a larger bodies. So this is called the planetesimal accretion, you can see here. And finally, they grow large enough. And during this time, its outer part was kind of a magma ocean. For example, our Earth formed like this, the collision of materials, and it was a magma ocean before. And what happened next is the primary differentiation process. What happens? More heavier elements, for example, nickel, iron, they sink into the center of that planetary body. For example, our Earth, and it started to form core, and more lighter elements form, like a mantle, and more lighter elements, even more lighter elements form the thin veneer of the brittle rock material, the analogy of the egg you can take. So it has a red inner one, so that is core, and there's a fluid membrane, so that is, you can consider it as a mantle, and then a thin brittle outer shell of the egg, so that is the crust. Here it is forming like that. So that's how, when we consider here, so this is a mantle here, so it's a convective flow, it rather act like a fluid. With the temperature, it will start a convective flow, and the iron is sinking downwards into the core. And this particular process is called iron catastrophe at this point of time. And that's how the primary differentiation results into the terrestrial planets. So this is an immediate comparison between the interior of the Earth. From the surface, you can see here. So this is the crust, the gray part is the crust. And here you can see upper mantle up to a particular depth of about 670 kilometers. Then about 670 kilometers to about 2,800 kilometers, you can see the lower mantle. So there is basically mantle has been divided into upper mantle and lower mantle. And then you have a fluid outer core. There is a fluid outer core, and there is a solid inner core. So the core's composition is mainly nickel and iron. So what about the Mars? So this is the interior, the cross-section, if you can imagine, cross-section of the Mars. You can see here again, there is a crust, and there is a mantle, and there is a core. So that core can be solid or liquid. There is a question mark for that. There is a reason why they have added this question mark, why they are not very sure about that. Okay, in the moon, you can, again, the crust is there. There is a mantle, and of course, there is a core. Okay, so the fluid outer core starts from 1,410 kilometers. Again, one more thing I would like to draw your attention here on the crust of the Earth. See, there are two kinds of crust, right? One is continental crust. That is, you can see that it is somewhat thicker, about 30 to 50 kilometers thickness of this crust. But oceanic crust is very thin one, 5 to 15 kilometers. So there is a dichotomy, crustal dichotomy on Earth. What about on Mars? No, there is no oceanic, or no, there is no continental crust. Everything is basaltic in nature. See, there is only one crust you can observe. There is no compositional difference. But on Moon, again, this is basaltic crust. So only on Earth, as of now, we could observe this variation, continental crust and oceanic crust, and they have a difference in composition. We will look into this one in detail in the upcoming slides. So all of you know what it is. What is that? So that is our Earth, our Mother Earth, right? Okay. Well, what is that? Can anyone answer? Hello?
Proto-Earth.
Okay, so what kind of Earth it is? What kind of model? Okay, this is called geoid model. So we have different mathematical models to project our Earth. Actually, our Earth is not a complete spheroid, it is oblate spheroid. So consider this as the core, not on the surface, but on the interior core. Okay, and from there, so this is the equatorial radius. You can see this is about like 6,378 kilometers, and this is about 6,356 kilometers. That means what? Equatorial radius is greater than the polar radius, right? We can just imagine this one, or we can figure out this one with the amount of gravity here. So gravity, you know, its value is average value is 9.81 meter per second square on Earth. But according to the gravity formulae, the Newton's law of universal gravitation, if you take that formulae, what is the formulae? F equals G times M1, M2 times R to the power minus 2. So R is the radius of the body, right? M1 is the M1 and M2 are two different bodies, mass of two different bodies, and G is the universal gravitational constant whose values has been given here. So that means the radius is inversely proportional to the force of gravity. So that means if the radius increases, force of gravity decreases, right? So you can figure out this one here. So equatorial gravity, you can see a 9.78 meter per second square. Polar gravity is greater than that of the equatorial gravity. This is the reason, because here the radius is lesser than that of the equatorial radius. So it will have a more gravitational attraction and more gravity it will show over there, right? And when we consider the...
Sir,
yeah.
What do the colors represent?
Pardon?
What do the colors represent in the picture?
All right, so this is a geoid model. This is like so this is actual, I can see here. So this is the actual Earth. So this blue colors are indicating like the oceanic lithosphere where the ocean exists. So the ocean water has been considered as the datum level, because we always measure the elevation based on the ocean water level, sea water level, right? So this is actually the globe indicating the equipotential surfaces, the surfaces with where the mean sea level matches with that one. So there is another model which will have an ellipsoidal model. So that will have more like a elliptical one. And this is actually indicating the different geoidal values. So for example, there is a low geoidal values south of the India. So people still wonder why there is a low geoid value over here in this area. People propose different ideas. And here there is a geoid bulge over there, which is indicated by the red color. So these are like mathematical model, right?
Yes.
Yes. Okay, so let's see the elevation on the surface of the Earth. I told you, this is the mean sea level that we consider as a datum, that is the 0 kilometers. And you can see here, which is the highest point on Earth. Someone?
Mount Everest.
Mount Everest, of course, you can see the Mount Everest over here. What is the value here? 8.85 kilometers. You know, that is the elevation of the Mount Everest, right? But what is the lowest point, the deeper point on Earth?
Mariana Trench.
Mariana Trench. Excellent. So what is the deepest, how deep it is? About 11 kilometers. That means if you just sink Mount Everest into the Challenger depth, then it will completely sink over there, right? So because it is 11 kilometers deep in the Mariana Trench. Well, now let's move on to the moon, our moon. So how our moon formed? So there are different hypotheses for the formation of the moon. One is the capsule theory. That means the moon was an itinerant body. It was an outside body which came into the gravitational field of the Earth, and it became the part of, it started like rotating or revolving around the Earth. So that is the capsule theory. The another one is the accretion hypothesis. It suggests moon was co-formed with Earth. That means when the Earth was evolving as a planetary body, the leftover materials, they formed as within the gravitational field of the Earth. The moon just started to accreting and the form, but it could not evolve as a larger planet. It formed as a moon, a smaller planet, so it just fall within the gravitational field of the Earth. The third one is probably the widely accepted one. This is the giant collision theory. What it says, there was a large planetary mass. The theory says as large as the size of a Mars, a planetary body that collided with the Earth. And this planetary body they call it Theia. So that is a body. So that collided with Earth, and the chunks of materials they just ejected from the Earth outer surface. That's important to consider. You can see that. So these materials, dust and rock materials, they radiated away from the Earth, and they formed as a disc-shaped geometry. And majority of ejected materials went into the circular orbit around the Earth, forming a clumsy, dense, donut-shaped ring. Sorry, and finally, what happened? I'm sorry. Yeah. Okay. Finally, what happens? These rocks, the dusty particles, they grew by mutual collisions. Again, accretions happened, and they formed like a single body over that ring, and that started revolving around the Earth, and that formed our moon. So this was the widely accepted theory of the moon. So when we just look onto the moon from the Earth, we can only see the inner face of the moon. We cannot see the outer face because the moon is revolving in the same speed. It is rotating as that of the Earth. So a revolving speed. So they match. So we can only see the inner face of the moon. And the moon is having an elliptical orbit around the Earth. So that means in one side, it is having a lesser distance than that of the other side. Okay, so this lesser distance side is called perigee, and when it is far away from the moon, that we call it as apogee, right? So this is the near side of the moon. That means we always see this side of the moon, and this is far side. What is this color indicates? This is the topography of the moon. See topography shades, they vary from blue or violet blue to as much as a red to white color in saturation, right? So from -6 kilometers to +7 kilometers, it varies. 0 is the datum level, right? So for example, all these areas, this is a depression, right? This is a low elevated area, or this is a depression, and this is a high elevated area. So there is a dichotomy, lunar dichotomy, right? So there is a depression and there is a elevated land over there. And when we see the near side, you can see there are a lot of large depressions. Can anyone tell how these depressions form? They are called mare. Mare means sea. That's the meaning of that, because initially in the 17th century, when people started to map the moon, they thought they must be filled with water, lunar water. So they thought they are the sea. So that's why the mere, the word came, I think, from the French word, I guess. So, but there is no water in this one. Today we know about it, but they are the large depressions formed by the impact of meteorites. The meteorite impacts created all this one. So here you can see there are many larger meteorite impact craters, and there are smaller craters as well, And so far, near side is having more craters or more mares than that of the far side. And in the south, there is a South Pole Icon Basin. So people think like a really large meteorite, a metallic meteorite, nickel and iron composition meteorite, just impacted onto the southern pole of this moon, and that formed this Icon, South Pole Icon Basin. The moon it's very interesting, actually, the composition of the moon, the rocks of the moon. So there are only two types of rocks. One is the lighter colored or the white colored rock. Another one is the darker colored. Two contrasting rock types it is composed of. So this lighter rock is called anorthosite, lunar anorthosite sample. So these samples have retrieved from the Apollo mission. So they just taken from the moon during the Apollo mission. So mostly this elevated land is composed of these lighter materials. That's why when we see the moon, we can see the lighter part as well as some darker part as well. Why? Because this mare region, the darker parts are composed mainly of the basalt. So this is called the darker rocks called basalt. We also have the anorthosite and basalt on Earth, but Earth is having very variety of rock types, not only these two rock types, but moon is having only these two rock types. That point has to be noted. Let's move on to the Mars. So that is the topography of Mars. Wow, Mars is really an exotic planet. Why? Because you can see here some of the elevated. So these are the volcanoes on the Mars. So there is a triplet of volcano and there is a single volcano, and this is the Mount Olympus volcano, and its elevation is not 14 kilometers, it is more than 21 kilometers. 21 kilometers. Our Mount Everest is just about 8.5 kilometers. You can imagine how big is this one. So, well, let's move on. All these points, the sites are indicating the sites of the Mars missions, like Viking, Pathfinder, Opportunity. Perseverance was the very last mission, if you remember. It has been launched in 2020s. So that was the Perseverance. And so you can see here, there is a larger fracture kind of feature on the Mars, right? So this is about 4,000 kilometers long fracture system on the Mars, and this is the one of the highest or longest fracture system in the entire solar system. We do have fracture systems or rift systems on Earth, but this one is really large in size. And these triplets, volcanic triplets, these are the individual volcanoes in triplet form, and they are called the Tharsis Montes, and this is the Olympus Mons, the largest volcano on our solar system, and this is the second largest volcano, Elysium Mons, and there are many other like smaller volcanoes as well, like Uranus, Patera, Tharsis Tholus, and there are some ridge formations, Claritas, Thomesia, Rice kind of ridge formations, and there are impact craters, like those are called planitia. Like on the moon, the impact craters are there, no? The depressions. They're called, for example, Hellas Planitia, Arger Planitia, Utopia Planitia, or those are the impact site. But by looking onto this map, what you can immediately see is a dichotomy, right? The northern portion is having it is a lowland, and the southern portion is relatively highland, right? So there is a lowland highland dichotomy over there on the Mars. So how this lowland highland dichotomy formed? This is a question. So this is the one of the Mars mission photographs. What you are seeing is like a basaltic rocks, so basalts, the dark colored rocks, the fine grained rocks on the surface of the Mars. And this one is the meteorites ejected from the Mars, and it came onto the Earth. It fell on the Earth, from the Mars out space. This is a meteorite, and all these are showing like the Mars is composed entirely of the basalt. Some people propose some different ideas, but eventually they failed, it seems like, but it is mostly composed of basalt. So the point has to be noted like the moon is composed of two rock types, anorthosite and basalt. Mars is entirely composed of basalt. And Earth, there are very many different kinds of rocks. You can see around many different shades of rocks. If you take igneous rocks means those formed from the magma, a molten rocky materials. When it will consolidate, it will form a rocky material. And you can see dark colored rock like granites, gabbro, basalt, andesites. So many different kinds of rocks you can observe on Earth. So why only a certain rock types occurs on other nearby planetary bodies like Mars and Moon? Why variety of rock types occurs on Earth? Anyone has any guess? If we are on the same page. Hope you got my question. Okay, anyway, let's see. We will get an answer hopefully at the end of this lecture. So that is the interior of the Earth from the surface. We know that there is a core, inner core that is solid, outer core is liquid, and there is a mantle. There is the lower mantle and upper mantle, and there is a brittle outer shell of rocky materials. So that will include the crust and uppermost part of the upper mantle. Okay, so this is the thing. So there is a continent. You can see the mountains over here. So this is the continental crust. The composition of the continental crust is the lighter or the lighter density rocks. Those are the granites. And this is the thinner crust, that is the oceanic crust beneath the ocean water, and that is composed of the darker rocks, or called the basalts. Those are the mafic rocks, and this the continental materials are, or the crust is composed of the felsic rocks, or the lighter or white colored rocks, you can say like that. Since I think the students from other than the geology background are also there, so that's why I'm just trying to explain in that way. Okay, and when you're just coming downwards, so this is crust, and this is the uppermost part of the upper mantle. Up to this one, this is very solid. This is brittle. This is rocky materials, completely kind of rocks. So, but after that, there is a slight difference. It behaves like a plastic membrane. Okay, this is called the asthenosphere. And after that, again, the mantle is continuing into different layers. And finally, about 2,900 kilometers, you reach the outer core, and that is a liquid outer core. And after that, you can see the solid inner over there. And this is the composition of the entire Earth. If you take the different elements, you can see that about 46.6% of the crust is composed of oxygen. About 43% of mantle is composed of oxygen. But in the core, about 30% is composed of oxygen. Oxygen is leading in composition in Earth, right? The next is silicon. You can see that the silicon is varying from 27 kilometers to mantle 21 to 15. Iron is very less in the crust, is slightly more in the mantle, but see, in the core, it is mostly composed of the iron. About 32% it is iron. And so that if you take each element, for example, if you take magnesium, it is very less in the crust, and magnesium is 22% in the mantle. In the mantle, magnesium is very high, and it is relatively less in the core. So the core part is mostly composed of iron and nickel. That's why it is called like that. Well, how you know about all those? You see, I said, like, outer core is liquid, inner core is solid, and there is a plastic fluid membrane, asthenosphere. How we know about this one? Can somebody know these things? Can somebody drill the earth into the core and go and see what is happening there? Is that possible? How we can evidence this one? See, we deals with the science, so we need the proof. What would be the proof for this one? Anyone?
Measurement of wave velocities.
What wave velocity?
Earthquake wave velocities.
Earthquake wave. Excellent, excellent. Thank you. So my friend told, like, seismic wave velocities. But before that, you should understand the pioneers who defined the interior of the Earth. For example, in 1897, Emil Wishart. So he calculated the layered Earth, the layered nature of the Earth. 1906, Oldham, he first proposed that there is a core. Okay, and core is 2,900 kilometers deep, defined by Gutenberg. Core is liquid. The outer core is liquid by Jeffrey's idea. So there is a solid inner core proposed by Lehman in 1937. And there is a crust mantle boundary proposed by Mohorovičić. So this boundary has been named after this Mohorovičić as Mohorovičić boundary, right? Now let's move on. As our friend told, like, the earthquake waves. How these earthquake waves are useful. Okay, everyone know what is earthquake, right? So they are the vibrations that is a faulting occurs within the earth, and when the rocks ruptures, they will tend to find a balance between them. The rebound will, and that will generate a lot of energy. The stress will accumulate over decades in rocks, and finally that will fault or rupture. This stored energy will release all of a sudden, right, into temperature and into vibrations and in the form of waves. So these are the different forms of waves are just depicted over here. Mainly these earthquake waves, or rather they called seismic waves. Okay, we can decompose or classify these waves into different waves. What is the primary wave? Then the secondary waves or S waves. Then the body waves. Those include, the surface waves, those include the love waves and Rayleigh waves, like that. So what it is depicting here is the motion of these waves. So for example, the primary waves moves like a compressive motion, just like a spring. Just compress, then dilate, compress, dilate. But you can see here, S waves are moved like S-shaped patterns. It will just a wave like ocean wave-like patterns. And love waves, a lateral motion is there. And Rayleigh waves, again, kind of a circular orbital motion is there. So these differential motions are actually causing the destruction of much of the buildings. Even Japan, it's very familiar, so we have many earthquakes yearly happening over there. So, and those destructions are mostly caused by the surface waves. But the body waves, P and S waves, are very, very useful for us, because these are the proxies for us to understand, to scan the interior structure of the Earth. How? Because the P waves are having higher velocity. So this is the formula for the velocity of the primary waves. What is that? K plus 4/3 mu by rho. What is K? Is the bulk modulus. That is the modulity of incompressibility. Mu is the shear modulus of rigidity. Rho is the density of the material. So density of the material shear modulus and bulk modulus defines the velocity of the primary waves. So, but the secondary waves are the slow waves, though I mean, in a seismogram, when we record the seismic waves, primary waves will first arrive there because their velocity is more. Secondary waves, they are the slow waves. They will just hit after the primary waves. It is showing here. This is the nature of the primary wave there. And its velocity formula has been defined by mu by rho. What is mu? Shear modulus. Rho is the density. Okay. Can someone tell me which material is having more shear modulus? A solid material or a liquid material? Because it is called modulus of rigidity, you know, which material is having rigid in nature and which is less?
Solid.
Solid is having high shear modulus, right? Because it is rigid than the liquid, right? Right? Okay, so in that case, you can see here, these primary waves can pass into solid and liquid medium, but can, according to this formula, can the secondary waves can pass through the liquid medium? Is that possible? No, because the formula is like this is in the numerator. When mu, the shear modulus for the liquid, shear modulus is 0, right? Then the entire term will be 0. That means shear waves cannot pass through the liquid medium, correct? So this is the idea, fundamental idea, proof to defining different layers here. For example, this is the seismic velocity through the interior of the Earth from 0. 0 is the surface where we stand now. And to the depth wise, up to 600 kilometers projected here, and up to 6,000 kilometers, 6,300 something. So that is the radius of the Earth. Okay. So here you can see that from the starting, the velocity is less at the surface, and the velocity, this is the blue line is the shear wave, and this is the primary wave, right? Primary wave is increasing velocity, and here also it is increasing, and at about 100 kilometers it is decreasing back, right? And again, see, this is about 1,000 kilometers, again it is increasing, and about 3,000 kilometers, about 2,800 kilometers, what is happening is, see, the primary wave velocity is drastically decreasing, secondary wave is breaking there is no secondary wave. What does that mean? This indicates like this medium could be liquid. That's why it is not passing, because shear wave modulus is 0 over there. And primary waves can still pass according to the equation, right? It can still have some values over there. So it can still pass, but in the inner core boundary, you can see that the velocity of primary waves again increasing and increasing like that. So this is why the scientists consider the inner core is solid and outer core is liquid. And the outer core is liquid. That's why one of the inherent property of the Earth is happening. Can somebody tell me what it is that? The inherent property because of this core dynamics of Earth. If you take a compass veritable point, why it is pointing north, a compass always north-south? So there is a property, geomagnetism. We have geomagnetism on Earth, but we don't have geomagnetism on Mars. It was there previously, but now it is extinct, but we still have geomagnetism. So this is the reason, because outer core is liquid, it will act like a convective motion around. The inner core is metal, iron and nickel. So this is a convective motion. It's like a current around a metal object, and that will generate electricity, and that will generate the magnetism. And that's why our Earth is having geomagnetism. This is another proof. Geomagnetism is another proof to prove that the outer core is liquid. Okay, so when we consider this structure, we will see like, from the crust, it is increasing, it is increasing up to this one. See, what is happening here is continental crust and oceanic crust is there. And after that lithosphere, sorry. So there is an increase, sudden increase in the seismic wave velocity that is marked by a boundary there, or a discontinuity rather. So this discontinuity separates the crust from the underlying mantle, because the underlying mantle is having denser rocks. The mantle rock type is called peridotite, so it is olivine-rich rock. But this crust is mainly composed of quartz, feldspar kind of lighter rocks. So when the seismic waves pass from the crust to the upper mantle, it should increase the velocity. And that's what you are just observing here, increasing velocity, right? So up to 100 kilometers, you can see here it is written as lithosphere. What does that mean? Up to this depth, it is composed of the brittle rocks, right? So the lithosphere is the term that indicates the crust and the uppermost part of the upper mantle part, right? And after that, there is a low velocity zone. You can see here, the velocity is decreasing here. Why? Because this particular layer is acting as a partial melting of rocks is happening there, or it is acting as a plastic beaker. Plastic rocks are here, more like a fluid nature kind of rocks. So that's why the seismic velocity is decreasing over there. And this particular lithosphere is floating over this plastic membrane, just like a ship floating, or a wooden block floating on the water on a sea, something like that. You can make the analogy. It's like that, it's floating over there. And on Earth, this lithosphere has been broken into several pieces. So before that, I think there are a few more slides. It is explaining the composition of the Earth's crust. So this is the continental crust. This is granitic in nature. For example, if you can see me here, can you see the rock on my hand? Can you see?
Yes.
Yeah. So this is the lighter color one, and this is a darker one, right? So this is the continental composition. Rather like it's a granitic composition, and this is a basaltic, or you can say gabbroic composition, this one. So the upper crust material here, the upper crust is the white colored rock, or the lighter colored rocks, that is the granite, and its density is 2.7 gram per centimeter cube, while the lower crust is like the darker one, and that is having about 2.8 to 2.9 or rather 3 gram per centimeter cube. That's one. In the mantle, there is another rock type that is called peridotite. Okay, it is like that. So the continental crust is the thicker one, 70 kilometers, where we can expect the maximum crustal thickness on continents in the mountain areas. For example, Himalaya is having highest crustal thickness, 70 to 80 kilometers. You can expect the crustal thickness over there. But in the oceans, it will be generally 5 to 10 kilometers. That's the crustal thickness. And this is the Moho boundary here. What you are seeing is a Moho boundary, where the seismic jump occurs from 6 kilometer per second to about 8. So that is the velocity jump occurs according to the higher density. It is like that. So this is the granite, the continents, and the ocean areas is indicated by the basaltic in composition, right? Well, these are the crustal abundance of elements. Oxygen is leading, 46.6%. Then here comes the silicon, 27%. Then aluminum, iron, calcium, and all. Right. So I'm skipping the Moho boundary and all those things. Well, let's move on. The lithosphere. So you know what is lithosphere? You know that this is crust and uppermost part of the upper mantle. This is the rigid rocky layer. floating over the low velocity zone called asthenosphere, like that. So the oceanic lithosphere has an average thickness of 100 kilometers, while the continental lithosphere 200 kilometers, up to 200 kilometers, the lithosphere can exist. It is like that. But there is a property for the lithosphere, for the continental and oceanic lithosphere. They have a different property. The continental lithosphere is composed of different layers, multiple layers. It's having a complex, complicated rheology. What is rheology? The ability to flow, right? Ability to deform. That is called the rheology, right? So you know about the Hooke's law, the brittle to ductile plastic transformation, how it forms like that. The same here, when the temperature increases, for example, here, you can see the graph. The x-axis is rock strength. Rock strength increases towards this side, and this is the depth. So from the surface, this is a 0 kilometers depth. So from that, you can see that initially, the rock strength is increasing. Up to about 15 kilometers depth, it is increasing, and then it is decreasing. Why? Because the crust is mostly composed of quartz and feldspar. It can behave brittle in the upper crustal areas, but as the temperature increases, it will lose the strength, and that is actually showing here. Again, the strength increases here. Why? Because there's a compositional change occurs in the mantle, uppermost part of the mantle, where the peridotite is the rock type, olivine is the major rock types. Olivine is stable at this particular depth and temperature, but at this particular depth, it is losing its stability, losing its strength, and the strength is decreasing like that, right? So that the continental lithosphere is having a multi-layered rheology. It's very complex composition of layers. But in the oceanic layer, it is having very simple, because ocean is composed of, like oceanic lithosphere is mostly composed of the basaltic in composition, mostly they composed of olivine and like plagioclase, clinopyroxene. So these are stable at a wide range of depth. And after that, a brittle failure is happening, and after that, strength is decreasing. So oceanic lithosphere is having very simple rheology when compared to the continental lithosphere. That's the idea shown here. I told you, like this lithosphere, this particular lithospheric layer is floating over the asthenosphere, has been broken into several lithospheric plates. That's what's showing here. These red lines are indicating the boundaries of the lithospheric plates. So there are many major plates. For example, this is North American plate. This is a continental plate. South American plate. This is a continental plate. Then African plate is there. Eurasian plate is there. Indo-Australian plates are there. So all those things are the major plates. Minor plates, like there are Nazca plate, Caribbean plates. They are the small sized plates. But all these lithospheric, the shell has been broken into several plates, and not only broken, they are in constant motion. They are just moving away from each other, or sometimes they're moving towards each other. When they move towards each other, what will happen? They will collide, right? One of the plate will destruct. Other plate will survive. When they just move away from each other, what will happen? The underlying magma will ooze out, right? So it is like that. So these particular lines are indicating, for example, you can see the mid-Atlantic ridge, this one. This is called a mid-oceanic ridge. So if you can see the sense of motion here, see, it is away from each other. That means from this boundary, two plates are moving away from each other along a fracture zone, right? So when they move away from each other, what will happen? The new magma material will come, and that will solidify, and that will form as a new crustal material. New crust is generating from here, and this particular boundary is called diverging boundary, right? Or constructive boundary. There, the construction is occurring. But when they just move into some other plate, for example, here, the sense of motion is towards each other, right? That what will happen? A more denser plate when it will meet a less denser plate. For example, an oceanic plate, it's a denser plate in composition. It will meet with a continental plate. What will happen? This denser plate will go beneath the lighter plates. It's called subduction. So this is active boundary. So where two plates meet each other, right? So this kind of process is called, what is the phenomena? The motion of the plates. Can someone tell? Plate tectonics. The plate tectonics is actually keeping our Earth alive. Why our Earth is dynamic? The ultimate answer is plate tectonics. So here again, these values are indicating the plate motion in respective areas. For example, in some areas, you can see 16.3 centimeter per year, and some areas it is like 1.4. Very slow spreading is happening. It's like that. Okay. So the mantle convection. So this is the crust floating on the mantle. So in the mantle, there is a convective current. So this convective current is actually dragging this plate away or towards each other. So this is the current motion that is enabling the plate to move away from each other or towards each other. Just like a hot plate in which a beaker of water will have a convective motion, Similarly, the mantle has the convective motion that shapes the Earth. So this is showing here. So different plate boundaries. This is a mid-oceanic ridge where the convective cells, the magma is coming up and it is oozing out, forming new crust. And again, it is just moving away to each other. And when it will meet with another plate, and the denser plate will subduct beneath the other one. It will sink beneath the other one, and it will again melt, and new magma will form, and that will rise up like that. So the basic forces here is the ridge push force and the slab pull force. Here, ridge is pushing away from each other by the upcoming or upwelling mantle currents, But here, slab is pulling down into the mantle. So that is slab pull force. These are the basic forces. But moving on to the plate boundaries, the first type of plate boundary is the divergent plate boundary. So this is the mid-Atlantic Ocean ridge. You can see here, it is passing through the Iceland area, mid-Atlantic ridge, What is happening here is, here the new ocean crust is forming. How? So this is the asthenosphere and this is the lithosphere. So this is the fracture zone. This ridge structure is a fracture zone. This is called the mid-oceanic ridges, through which the magma is upwelling and it is accreting over here, and it is pushing the slabs each other away from each other, and new magma material is accreting over there, and new basaltic, this is basaltic magma. Mantle melt will generate basaltic magma that is accreting over there, and that is pushing away each other, and the plate is moving away. Newly formed material will accrete here. After some time, it will move here, move here, move here, as the plate getting old. So this zone is called the divergent plate boundaries, or rather it is a constructive boundary. Whereas in some areas, as I told you, when plate moving, I'm not able to close this one. Please hold on. Anyway. Okay, so what is happening here? This is oceanic plate and this is a continental area. And what is happening is oceanic plate is meeting the continental area. What happens? Oceanic lithosphere is a denser lithosphere than the continental one. So it will sink downwards. So this is oceanic plate convergence, when two oceanic plates moving each other. Which ocean plate is having denser than the other one? That will sink down, that will subduct beneath. And as this plate will subduct, it will encounter greater depths and high temperature. It will start melt and it will generate magma, and that will rise up and that will form volcanic islands over there. This is called volcanic island arc. So there is a region behind the volcanic arc is called back arc region. And this is a fore arc region. This is the trench area, the suture zone. where two plates meet each other and one of the plates subducts beneath the other. And this is the continental oceanic crust. When these two crusts meet each other, of course, the oceanic crust, the denser plate will subduct beneath. Again, the subducting slab will melt and that will generate the magma and that will underplate. So this is the continental crust. It will underplate the continental crust, the magma, and it will just it will come up, and this magma will mix up with the continental crustal materials, and that will result into different compositions. For example, andesite is a rock. So this is called, if you can see here, this is an andesite I collected from Japan, Fuji mountain. So from there, so this is andesite. How they formed? The mantle derived the basaltic magma, when it will contaminate or it will mix up with the crustal melt. So crustal composition of granite, right? So when these two composition will just they mix together, that will form an intermediate composition, right? So that intermediate composition is the andesite rock. And here, what happens? It's like, when the ocean moves, what happens? There is a continent attached with this ocean that also trails this ocean. Finally, when the ocean crust completely consumed at the subduction zone, the trailing continent will collide with the overriding continental crust. So two continents are meeting here, converging here. What is the result? A huge mountain range, folded mountain range will form there. And this is how this particular mountain range formed. Which mountain range is that one? Himalaya. Himalaya formed by the collision of Eurasian plate and the Indian plate. So this is demonstrated here. Indian plate was somewhere in the southern latitude. It was aligned with Antarctica, Australia, Madagascar, Africa, and all. And from there, Indian plate just rifted from these continental masses, and then it is drifted northward, and finally it is collided with the Eurasian plate. And during that collision, what happened? The higher mountain ranges, the folded mountains formed, and that's how the Himalaya formed over there. Well, there is another particular boundary where no destruction nor construction happening. Only two plates slide past each other. For example, San Andreas Fault. You might be knowing about the San Andreas Fault earthquakes, Chile earthquakes, and all those things. Those happened due to this faulting. The slide past each other, the fault generated by that one. Okay, that's a third kind of boundary. So what is the fate of a subducted slab? We know that one of the plates, ocean plate subducts beneath the lighter, denser, lighter continental plate. What happens? This plate is subducting, and it is reaching, see, up to the lower mantle. It reached up to the core mantle boundary. Okay, so this is a seismic imaging, like we do the CT scan of our brain scanning, like that we can do the tomography imaging of the seismic wave velocities. So this particular blue shade is indicating like a colder material, and this is the hotter material. What is happening is the subducting slab is just detaching. This slab is detaching, and it is breaking, and it is just sinking down, and it is reaching in the core mantle boundary. And there again, it is melting completely, and that melting material is rising up. Okay, rising up. So from the core mantle boundary, hot plume materials, it can rise and it can reach up to the surface, and it can generate volcanisms. So volcanisms can form either by the divergent plate boundary or the convergent plate boundary, from which the volcanic arcs will form, and then by the deeper source of plumes. So this is called plume. When it will reach at the surface, that will form the hotspots, So these are the hotspots. This is the core, the mantle boundary, and from which the hot material, see the plume head, it is rising, reaching at the surface of the earth, and it is just outbursting a lot of like continental flood basalts. For example, Deccan volcanic province in India is the best example for this kind of a plume volcanisms. So these are called large igneous provinces when this kind of igneous provinces will form. So these all are indicating hotspot volcanisms. Okay, so these hotspots are constant bodies over which the plates will move. The hotspots will remain the magma source, but the plate is in constant motion, right? So when it will move, new volcano will form, then it will move, the next volcano will form like that. And the best example is the Hawaiian Emperor Sea chain. You can see here, the ridge forming here. Okay, when you see the age, so this is the age of these independent mountains. When you see, you can see an interesting thing. So the northernmost island is having 64.7 million years old, but the southernmost island, Kilauea, so it is showing 0 million years. That means the hotspot is located somewhere here in this area. So this was the first island formed. That means plate moved through that way, through this line like that, right? So this is the active hotspot region over there. So that's why it is showing 0 million years. That means today, age today, correct? Right. So, you know what is this figure, 4,500 MA, 4,500 MA. What is that? What is the significance of that age? Hello?
Age of Earth.
Age of Earth. Not only Earth, the solar system, we can say, correct? Yes. So this is the oldest drop, what you're seeing on Earth, right? How you will get the age from this one? There are different techniques, but mostly this is a particular rock with a lot of bands are there, right? So this particular structure is called gneissic texture. So this rock is a gneiss, and from this rock, the scientists, the geologists, they extracted or they calculated the age of this rock. How they have calculated? They have extracted a radioactive mineral, which is called zircon, from these rock types. Probably I can, yeah. So this is a zircon. This is a tiny fragment zircon. We cannot see with the naked eyes. Under the microscope, we have to, first we have to crush the rock and we have to take that powder, and from that we can separate the zircons under the microscope, and that zircon is, this particular grain is having enriched with the radioactive elements like uranium, lead, and all. So uranium is a radioactive mineral, and that will decay into lead. We know the decay constant and all. So by estimating that decay period, we can calculate the age. So this is the calculated age. This is the Concordia diagram, what you are seeing. So this is the uranium-lead ratio they have taken to plot this one. And the oldest age is given here for this particular rock is about 4,000 to around 4,000 MA, right? 4,002 to 4,031 MA, right? But the age of the Earth is 4,500 MA. Why then? It should be ideally, it should show the oldest rock like 4,500 MA, right? Why it is having less age? Anyone? Okay, the answer is that the Earth is dynamic. Okay, because it is continuously renewing its surface by internal and external processes. Weathering processes is the internal processes. External process. Internal process, like the subduction is happening. The older materials are subducting beneath, and new magma is generating, and that is partially melting the already existing rocks. So these are happening continuously on Earth. That's why the older materials are not surviving. This is the age of the oceanic lithosphere. You can see that these lines are the mid-oceanic ridges where new crust is forming, where the age is 0 million years. That means this is the newly formed crust over there. As you move away from the mid-oceanic ridges, age is progressively increasing. But maximum age is only 280 million years. Remember, the Earth's age is 4,500 million years. This is just 280 million years. So why the oceans are much younger than the continental lithospheres? The answer is oceanic lithosphere. They forms and they consumes, they subducts. So that convective motion is continuing on Earth. That plate tectonics is operating on Earth. That's why you are observing this kind of phenomenon. Well, sorry. Well, this is actually the age distributions. I told you about the zircon ages. So these are the zircon ages. See, this is number of samples, and this is age from 0 means today to the formation of the Earth. You can see the distribution of different ages. The red one is called the igneous zircon. That means the zircons collected from the igneous rocks, like granite, basalt, gabbro, this kind of rocks. Dipledal means they collected from like sedimentary rocks. You know, this volcanic rocks, after some time, with the surface processes, it will just weathered, it will disintegrate into sediments. So collected from the sediments. When they just plotted all together, they observed a particular peak in particular areas, in ages, particular ages. For example, 3.5 billion years or 3,500 million years, there is a small peak, a cluster. Another cluster is around 2.8 to 2.5 or 2,500 million years. Another peak is around 2 billion years, about 1800 to 2000 million years. And another peak is in 1000 around, then another peak is around 550 million years. So people were wondering, why this kind of clusters, what's the notion of this one? Then after extensive studies, the scientists, the geologists, they realized something is happening during this time. These are the periods of the abundant crustal production on Earth. That means at this particular point of time, a lot of crust formed. How the crust forms? There, our Earth is having a particular phenomena in which all the smaller continental materials will accrete together to form one giant continent, and that is called the supercontinent, right? So, for example, in 2.5 billion years, there was a giant supercontinent formation and a lot of subduction, a lot of magmatic igneous activity that produced a lot of new rocks, new crust formations happen, and that is indicated by this. And this particular supercontinent is called Kenor Land. And after that supercontinent formation, again, these continents will break up into separate fragments. For example, India, Antarctica, Australia, all those continents were together about 550 million years ago. And they just separated at about 200 million years ago. And finally, India separated from Madagascar and about 90 million years ago, and it is just moved northward and collided with the Eurasian plate like that. So this kind of process is happening. So there is another supercontinent called Nuna supercontinent around 1800, and then Rodinia 1100, and then Pangaea, the final supercontinent, the Gondwana land 550, and finally Pangaea. So Pangaea was the final, very recent supercontinent, about 200, less than 200 million years ago, this Pangaea existed too, right? Well, to show how these continents move, so this is just a demonstration. You can see in this particular supercontinent, see all the continents are aligned together in one place. For example, here, India and North China cratons they are just, aligned together. This is one of the models. And this is around, what million years? I'm sorry. Yeah, 2005 and 2200 years. Okay. So this is what happened. And after that, around 2000 billion years. Sorry. Yeah, 1000 million years. You can see that India has been moved here. North China is moved there. And about 540 billion years ago, that is the Gondwana supercontinent formations. You can see India has been aligned with East Africa, Antarctica, Australia, and all, but North China craton has been moved to that side, right? And in Pangaea time, India is here, and North China combined with the Mongolia. area. So this is how the continents move continuously over the time, and they just form supercontinent. So this is a Pangea, or rather Gondwana supercontinent assembly of India. So this is India. If you can see, imagine India is aligned with Madagascar, and Antarctica and Sri Lanka is in between. And what happened? India and Sri Lanka separated from Antarctica at about 120 billion years ago. And finally, India separated from Madagascar. It is like rifted from Madagascar and then drifted northwards, like that. So on Earth, so you can see a lot of colors, almost 700, more than 700 varieties of igneous rocks we can see on Earth, but that is absent on the other celestial bodies like Mars and Moon. What is making all those rocks? Actually, there are only very few, 1 or 2 parental magma source. That is the magma source is the mantle. So mantle rock is peridotite. When the peridotite melt, that will form the basaltic magma. That basaltic magma, when it will just come upwards, it will differentiate into different rock types, and already existing rocks will partially melt because of this heat source, and they will mix together to form another source. As I told you, how the andesites form in the continental like subduction zones, how the andesites form in the volcanic arc regions, right? So these andesites are absent in Mars or on Moon and all. Why? Because there is a reason. We will see that. On Earth, this kind of tectonic processes, they result and the magmatic differentiation, partial melting, all those processes are resulting into different varieties of rocks. Okay. Now coming on to the Moon. So we already discussed about the near side and far side topography and all. So this is the mare side in which basalt in composition, and this is the highland areas where the another side is the composition, the lighter colored rock or white colored rock, and this is the dark colored rock, basalt in these areas. Only 2 kinds of rocks. And this is the crustal thickness of Moon. If you see the near side of the area, you can see that the crustal thickness is lesser. It's about less than 40 kilometers, about 30 to 35 kilometers on an average. But on the far side, you can see the crustal thickness can go up to 60 kilometers. That is from the surface to the moho. That is the crustal thickness, moho boundary, right? So the far side, it is more. So one reason, again, still this is not yet proved or proposed firmly. Still debates exist on this, crustal variations, for the reason that the near side area is having many large impact craters. Probably this impact might have altered the crustal thickness. So where it has been impacted, so that crust has been remelted and formed like a mantle upwell, and it thinned out the crust over there. While the far side is having very less impact, comparatively lesser impact size, probably that's why it is having higher crustal thickness. That's one of the explanation for that one. And this is the lunar surface regolith and rocks composition. Again, SiO2, silicon dioxide, is more in composition in Maria and highlands. Both are having silica saturation. Then alumina is 14.9% in Maria, the depressions, and it is about 24% in the highlands. Iron is about 14% in Maria because that is basalt in composition. Basalt is having heavy elements like the iron and magnesium, so that it is having higher concentrations over there. So that is the so magnesium also, you can see, is higher in the Maria basalt region. In the anthocite highlands, it is less. So this is the immediate comparison between Earth and lunar lowland, lunar highland of element. I mean, for each element, for example, oxygen is leading on Earth and both in lunar lowland and highland regions. And then The next abundant element is the silicon and the aluminum, and so on. It's going like that. Coming on to the Mars, we know that there is a lowland, highland dichotomy. The northern portion is lowland. The recent researchers, they prove to be like the northern lowland area was an ocean once in a time. So, and there were many valley networks, many rivers and lakes were existed during the early stages of the Mars. But finally it probably its atmosphere, and all the gases, they just escaped into the space, and they could not survive the liquid water on the surface of water, and that's how it happened. So why this is a lowland and this is a highland? There are many theories, mainly like a mantle overturn is one of this theory, like mantle melting occurred in the northern lowlands and then the southern highlands, and that results into a lowland area over there. Its crustal thickness is also very less, the lowland area, compared to the highland, southern highland area. And this is the age map on the Mars. You can see that it is starting from 4500. That is the age of the Earth. Okay, up to the 0 has been given. There is different ages like pre-Noachian, Noachian, Hesperian, Amazonian. So these are the age ranges here. For example, all these green or reddish areas are like older regions, and these bluish areas are like slightly younger regions. So the northern lowlands, there is another theory like large impact, meteoritic impact caused this area where to form a lowland or a thinned crust in the northern lowland area. So that is another theory explaining that one. Okay. And this is the diagram. This is alkali versus silicon dioxide, SiO2 diagram. It is showing different rock compositions. So these are like Martian rocks, meteorites mainly, and also some rocks they have taken by the data by the hyperspectral, like spectral data, and like gamma ray spectrometer and all those kind of techniques they have used, and they just combined with the Martian meteoritic data. We don't have a Martian sample yet from Mars. Still, the upcoming mission will go there and collect the samples from the Perseverance mission. Perseverance mission is currently collecting the samples, pencil-sized samples from the surface of the Mars, and the next mission will go and collect those samples and come back. Then only we can have the hand specimen. Right now, what we have is a Martian meteorites, the fragments of Mars that is thrown into the outer space, and they catch into the gravitational field of the Earth, and they fall on the surface of the Earth. So those samples, they have plotted the geochemistry, SiO2 versus Na2 plus K2, and they find like all are inconsistent with the basaltic composition. But interestingly, there are some samples that is from the gamma ray spectroscopy data. They're falling in the andesite areas. See, this andesite rocks will form in the subduction zones, right? Arc magmatic zone, as we have seen on Earth. But on Mars, it is not reasonable. Recently, the researchers are saying like, these are the altered basalt. Sometimes altered basalt can give a biased signal of like a spectrum of that's similar to the andesite. Probably there's an andesite present over there. Yeah. Somebody ask something? Any questions? No? Okay. Sure. So this is the crustal thickness map of the Mars. You can see here, the crustal thickness is varying from around 10 kilometers to more than 110 kilometers. Really thick crust. When you take Earth, the maximum crustal thickness is 80 kilometers, and crustal thickness is more in the continental areas. These are the continental areas. The bluish and this reddish and yellowish reddish area is the Himalaya, where the crustal thickness is about 80 kilometers. But on Mars, and this violet area is the oceanic region, where the crustal thickness is less than 10 kilometers, right? We know what is the reason, the plate tectonic processes. That is the reason. So here, the crustal thickness is maximum in the volcanic area, the southern highland area. The Tarsus volcanic province here, this is Olympus Mons. They are showing the higher crustal thickness of more than 110 kilometers or more than 100 kilometers. And the northern lowland, the crustal thickness is really less than 20 kilometers. So where this giant impact, meteoritic impact happened, these are starkly showing very thin crust because of the impact, the mantle of upwell and the crust has been thinned out. That is what happened in this area. So we know this is Earth, and this is half the size of the Earth, that is Mars. And we know that on Earth, the process, the phenomenon is the plate tectonics. The slab is generating at the mid-oceanic ridges, and it is sinking, subducting in the subduction zones. But on Mars, we don't have any evidence for plate tectonics because only basaltic rock exists over there. And where we propose like a plume tectonic model. What is plume? I have already explained you. From the core mantle boundary, the plume is rising, and that is just accreting at the base of the lithosphere. And from that basaltic lava or magma is forming, and from that basalt is forming there. And this is in this one, in this model, what is happening? Plates are constantly moving, but here there is no plates constant. There is no like broken plates. Everything is like a single plate existing as a single plate. So plate is not moving, but the magma is continuously upwelling, and that is feeding the volcanoes. And that's why the volcanoes are getting in larger size, that's why the Olympus Mons is growing like 21 kilometers high, because it is not moving from the source. It is just standing over there on the top of that magma source, plume source, and it will eventually grow bigger and bigger. And that's how we can define the Martian lithospheric evolution and Earth's lithospheric evolution. And here, there is a major events of the Earth and Mars has been demonstrated from 0 million, that is today, and towards 4.5 billion years. It is projected like that. So GOE at about 2.5 million years is the great oxidation event. After that, oxygen became abundant on the atmosphere on Earth. And after that, the features, biological features start to evolve. The life started to evolve after this one, mostly abundantly. And then about 3 million years, and there is oldest rock about 4 billion years or 4,000 million years, you will find the oldest rocks and all here. So after the great oxidation event, like different biogenic or biologic productions happened, and we exist today as humans. On the Mars, again 0 to 4.5. So what is happening here? So there is a magnetic field. So my personal research on Mars, we came into a conclusion like about in the older period up to say about 4.3 million years period, or 3 billion years, or 3.5 billion years period. Till that period, magnetic field existed on Mars, but eventually it lost. People assume like, okay, this is the reason, the result of giant meteoritic impact. Giant meteoritic impact has caused the magnetic features to lost, or another theory is like Martian outer liquid core has been dried out so that it cannot convolve, or it cannot form the currents, and and that's how the magnetism extinct on Mars. And during that and up to that period, probably an ocean existed in the northern lowlands of Mars, and many river systems, valley network, everything exists. And finally, after this period, probably the atmosphere lost on Mars, and the liquid water could not exist except in the polar regions as ice forms. And after that, the Mars became a dry planet, completely dead planet, and it exists as such till now. Probably our Earth's future could be just similar to the Mars. After some time, our Earth will also become like a graveyard. So that's all about this lecture. And I'm open to your questions. You can ask your questions. We can discuss if you have any. Hope you understood and enjoyed the lecture. At least I know that the people, other than the geology background, it will be slightly difficult to follow. But in an online lecture, this is what I can maximum offer to you. Yeah, over to you.
Thank you, Dr. Ratheesh, for the wonderful lecture. So students, please come up quickly with your questions because we are a little late. We will wait for a few more minutes. And
Sure.
There is one question in the chat.
Nathira, can you just read out that one?
Okay, sir, how do you determine the tectonic style of extraterrestrial planets? Is it based on surface morphology or on seismic structure?
Excellent question. Who asked this question?
Tirumala Vishnudeep.
Okay. Yeah, so how we can sense the tectonic style of the terrestrial bodies? So that's a question. Of course, from the surface geomorphology, we can understand, for example, there are surface features. On Earth, we have Himalaya. Okay, then people started to think why Himalaya formed. There are many earthquakes happening in the Himalaya. Then people started to think why it is a seismically active zone. Then then people started to examine what is there beneath the Himalaya. So then people just started to probe this crustal thickness of this Himalaya. They find, okay, it is having enormously thicker crust like that. Then they started to think then they have done the geological analysis. They have taken the rock samples from there, different rock samples, and then they have done the geochemical analysis, geochronological age dating analysis, and by all these analysis, not only by the geology, not only by the geomorphology, not only by geophysics, by a multidisciplinary aspect, they just came into the conclusion, okay, this is an active boundary area. And they then understood okay, Indian plate is a different plate than from the Eurasian plate. So they have a different entity. At a particular point of time, at about 50 million years ago, the Indian plate came towards the Eurasian plate, and they collided, and it resulted into the formation of the Himalaya. On Mars, of course, the same process we can just check. The geomorphologically, we can see a lot of rift valley. That Valles Marineris is a 4,000 kilometer long rift valley. So why this 4,000 kilometer rift valley is existed? Why this volcanoes, Olympus Mons or the Tharsis Mountains, they are attaining larger size than that of the Earth. So this was the geomorphological one. Then people started probing the internal structure, its composition and all. Then we will find, okay, it is only basalt, not much variations occurred there. Okay, so that means probably plate tectonic, evolved magma could not exist over there. So only basaltic magma evolved, and there is no plate, different rock and plates. Only some Martian quakes are there. So InSight mission, they have a single broadband seismic station over there. So they are getting data from there in the inside area. And they are probing the interior structure of the Mars, and they are recording the Mars peak, deeper Mars peaks. That is because of the temperature instabilities within the Mars happening. Otherwise, there is no plate tectonics. So answer is like, other than the Earth, no other planetary bodies till now, it is found to be having this plate tectonics. So that's why I would rather stress like plate tectonics is the reason for the life being existed on Earth. That is a fundamental phenomenon. Any other question?
No. Yeah, I think we can wind up.
Okay, sure. Thank you so much. Thank you for listening.
Thank you. Thank you so much.